page 109. All right, first half of section 1.4 is about combinations of functions. Second half is compositions of functions. So we are looking at combinations today. And they basically give me four formulas there on page 109. They give me a formula for the sum, difference, product, and quotient of two functions. And they're fairly straightforward. If they give me two functions, f of x and g of x, if I want to find the sum of those two functions, it's literally just f of x plus g of x, and we denote that f plus g of x. If I want to find the difference, f of x minus g of x, that's f minus g of x. Find the product, f of x times g of x, we write f times g of x. And find the quotient, f of x divided by g of x, we write that f divided by g of x, with the understanding that g of x can't be equal to 0, because of course our denominator can never equal 0. So this is not really a difficult concept. If there's anything that's challenging about it, it's the domain component of it. Because not only are they going to ask me to find those combinations, but they're also going to ask me to find the domain of the combination. And the domain of the combination is going to be the intersection of the domain of f of x and the domain of g of x. So I'll need to find the domain of those two individual functions and then just see where they both exist. Because, it makes sense. You can't add f of x and g of x if f of x doesn't exist at that spot. So you can only add them or subtract them or whatever the case may be where they both exist. So that's why we need to find the intersection of their domain. So if they told me that f of x was equal to 3x plus 2 and g of x was equal to x squared minus 2, and they asked me to find the sum, difference, product, and quotient of those two functions, then we can start off by saying, okay, if they want f plus g of x, that formula is f of x plus g of x, so I'm just going to take f of x and add g of x to it. And I'd want to do any simplifying that I can, so like positive 2 and negative 2, of course, would cancel each other out and leave me with just x squared plus 3x. But that would be the simplified sum. All right, then they asked me to find f minus g of x. So f minus g of x, of course, is f of x minus g of x. So I'm going to take the first function minus the second function. And remember that if you are subtracting that second function, you're going to need to distribute that negative through that second set of parentheses. So if we distribute that negative, we would have negative x squared, and then minus a negative, we'd have plus 2. So this time the 2 and the 2 would also combine, only instead of canceling each other out, they would combine to be 4. F times g of x, we just want to do f of x times g of x. And again, I want to give that answer in simplest form. So how am I going to give that in simplest form? What would I need to do? Yeah, FOIL it out. So we could go through then and we could say 3x times x squared is 3x cubed. 3x times negative 2. 2 times x squared, and 2 times negative 2. So we'll end up with 3x to the third, negative 6x, positive 2x squared, and negative 4. And nothing wrong with that, but when you look in the back of the book, they're always going to give the answer in descending power form, and that's typically the way that we write it as well. So I would just rewrite that so that it goes x to the third, x to the second, x to the first, no x. Not wrong if I don't reorder it that way, but that's just typically the way that we write it. All right, and then for the next one, they asked me to do f divided by g of x, so that's just f of x divided by g of x. So we'll take our f of x function and divide it by our g of x function. Now, if there was something in common in the numerator and the denominator that I could cancel, I would do that. I cannot cancel these x's. I cannot cancel these 2's. You can't cancel things that are being added and subtracted. You can only cancel things that are being multiplied. So if I could take a common factor of 2 out of that numerator and a common factor of 2 out of that denominator, then I could cancel it out. But since I can't do that, there's no way to simplify this or reduce that any further. That is in its lowest terms. So not only could they ask me to do the sum, difference, product, and quotient of the functions in terms of x, but they might also ask me to find it in terms of a numerical value. Like they give me f plus g of 2, all right? If I'm looking at f plus g of 2, well, if f plus g of x means f of x plus g of x, then for f plus g of 2, I'm just going to put 2 in the place of x. So I'm just going to find f of 2 and g of 2. So let's start with f of 2. What does f of 2 tell me to do? What does f of 2 tell me to do? Yeah, I'm going to put 2 in the place of x in this f function. So we're going to do the 2 times the 3 and then plus 2. So what would we get for f of 2? 8. And then we could do the same thing for g of 2. Put 2 in the place of x in the g function. So that would just be 2 squared minus 2. So 4 minus 2 would give us 2. And so f plus g of 2 is 10. Now that's one way we could do that problem. Another way that we could do that is we've already found f plus g, right? We had already done f plus g of x, and we had gotten that that was x squared plus 3x. So another way that you could do this problem is if you want f plus g of 2, you could just put 2 in the place of x in that sum formula that you've already found. So if you did that, you'd have 2 squared plus 3 times 2. That would also give you 10. So it doesn't matter which way you go, you're going to get the same answer either way. All right, then let's talk about the domain of those combinations, because we said that was the part that was going to be a little more difficult for us. So if I want to find the domain of the combination, I'm going to need to find the domain of f of x and the domain of g of x and see where they overlap. All right, so let's start with f of x. If I'm looking at 3x plus 2 and I'm trying to find the domain of that function, what is the domain of 3x plus 2? Well, we studied domain, over a month ago? It's been a little while, so let's review. Your domain is going to be all real numbers unless one of two things happens. Do you remember what those two things are that we had to watch out for? Okay, can't have 0 in the denominator. Square root of a negative. Nice. So we said the domain would be all real numbers unless you had 0 in the denominator or a negative under like a square root or a fourth root or something like that. Now, cube root of a negative was no problem at all, but square root or fourth root of a negative was where we ran into imaginaries and we had problems. So when I look at 3x plus 2, I don't have a denominator, so there's no chance of 0 in the denominator, and I don't have a radical, so there's no chance of a negative under that radical, so therefore my domain is going to be all real numbers. All right? How about x squared minus 2? What would that domain be? X squared minus 2, what would my domain be? All real numbers. Because again, no 0 in the denominator, no negative under a square root or a fourth root. So when I go to find the domain of my combination then, I'm going to find the intersection of all real numbers with all real numbers. So that's just all real numbers. So the domain for the sum and the difference and the product will be all real numbers. However, when I get to the quotient, remember that your denominator cannot be equal to 0. And the same thing is true when I'm looking for the intersection of those domains. I can't have a denominator of 0. So I may not have to make an exclusion for any other component, but I typically will for that quotient. I'll typically still have to make some type of an exclusion for my domain. So we're going to say that our denominator cannot be equal to 0. Our denominator was x squared minus 2. So x squared minus 2 can't be equal to 0. So let's solve that. Add 2 to both sides and take the square root of both sides. And that would give me plus or minus the square root of 2. So we could say all real numbers except for a positive and negative square root of 2. A lot of times they want that in interval notation. So if I were writing that in interval notation, I would say, okay, let's start over here with negative infinity, and we're fine until we get to that first excluded value, which is a negative square root of 2. I'm going to have to pick up and jump over that, and then I can keep going until I get to the next excluded value, which was a positive square root of 2. I'm going to pick up and jump over that, and then keep going, and there was nothing else to exclude, so I would keep going to infinity. So all real numbers except for positive and negative square root of 2, or if they want it in interval notation. All right, let's look at another one of those. Only this time they're going to give us a little more challenging equations to work with, specifically when we're looking for the domain of the combination. All right. Alright, so for the next two that we want to look at, they give us f of x is equal to the square root of x, and g of x is equal to the square root of 4 minus x squared. Alright, so go ahead and find your four combinations. Add your functions, subtract your functions, multiply your functions, and divide your functions. Okay, so let's see how you did. If we had f plus g, we're just going to take f of x plus g of x. Not really a way that I can combine those two radicals, so that is my answer. For f minus g, I'm going to do f of x minus g of x, and again, can't combine it, so I'm good. For f times g, that's f of x times g of x. When you have a radical times a radical, you can combine what's underneath your radical and multiply it. So in this case, it really didn't make that much of a difference. Like when I go through and distribute the x to the 4 minus x squared, it's not like it makes it something that then I can take the square root of or something. But, you know, in some cases, maybe I have a binomial times a binomial that then I can combine like terms in a trinomial, or maybe I get something that is a perfect square that I could then take the square root of. So it's always worth trying. And same idea with f divided by g. If you have a radical divided by a radical, you can combine that under one single radical, because then sometimes you're able to reduce that fraction. We weren't able to reduce this one, but sometimes you can. Typically, we would rationalize our denominator, but in this instance, you'll see them frequently leave that radical in the denominator just so that you can see, hey, this was f of x and this was g of x, and this is what we got when we combined it. So it's one of the few times that they do let us leave that radical in the denominator and not have to rationalize it. So the combinations, not too bad. What we want to look at is the domains. All right, so let's start with, remember we said the domain of the combination is going to be the domain of f of x intersected with the domain of g of x. So let's find the domain of f of x and the domain of g of x. All right, so starting with f of x, if we've got the square root of x, we said your domain is going to be all real numbers unless you have 0 in the denominator. Any chance of 0 in the denominator there? No, don't have a denominator, right? Or I also need to avoid a negative under a square root or a fourth root. Any chance of that? Absolutely. So remember we had said anytime you're trying to find the domain of a square root, take what is under your radical and set it greater than or equal to 0. Take what is under your radical and set it greater than or equal to 0. I don't want a negative under the radical, so it can be positive or it can be 0. To find the domain of a square root or a fourth root, take what is under your radical and set it greater than or equal to 0. Alright, same idea then for g of x, right? I have a radical, so let's take what's under our radical and set it greater than or equal to 0. However, when I do that for g of x, this is a polynomial inequality. We looked at polynomial inequalities in section P5, but that was a while ago, back before we ventured off to chapter 9 with probability and statistics and sequence and series and all that. So it's easy been over a month ago. So let's go back through that again. When you have a polynomial inequality, you have to make a sign graph. So step number 1 with a polynomial inequality is we set it equal to 0 and solved it, and the solutions that we got were our critical numbers for our sign graph. First thing with a polynomial inequality, I know it's a polynomial, it's not linear, it's not x to the first, it's x to the second, so I have to treat it differently. I'm going to set it equal to 0 and solve it. So when we solved, we got positive and negative 2, and we called those solutions critical numbers. All right, we're going to put those critical numbers on a number line, and that's the beginning of our sign graph. So basically, we just broke our number line up into 3 intervals. I have an interval over here, I have an interval in here in between the critical numbers, and I have another interval over here. Now remember, we had said every number within that interval will have the same sign, so that we could test just one number in that interval and it would tell us whether the whole interval is positive or negative or what. We called that a test point. So I like 0 as a test point. I'm going to take 0 and I'm going to plug it back into 4 minus x squared. So if I take 0 and I plug it back into 4 minus x squared, I get a positive 4. The 4 is irrelevant. The fact that I got a positive is what's important. So that means that this whole interval is positive. If you had chosen any number in that interval, 1, negative 1, 1.5, 1.9, 1.99, negative 1.9999, every single one of those is going to generate a positive value. You also could come over and pick a test point in this interval, like maybe you pick a positive 3, come over here, maybe you pick a negative 3, something like that. But we learned a shortcut with these sign graphs that every time we crossed a single critical number, the sign changed. So instead of having to test every interval, we said, okay, if it's positive right here and this is a single critical number, then I know my sign is going to change to negative in this interval. If this is positive here and I have a single critical number, when I cross over that, then I know that my sign is going to change. So I can use one test point and find out it's positive here, cross a single critical number, sign changes, cross a single critical number, sign changes. Now I've got my sign graph. So now I can go back to answer the question that was asked. In the very beginning, we said, where is 4 minus x squared greater than or equal to 0? What kind of numbers are greater than or equal to 0? Positive or negative? Positive, right. So I'm looking for this positive piece right here. That would be in between negative 2 and 2. So that is my domain for that function. So again, we did that extensively back in section P5, but that's been a little while, so we just wanted to go through that process again. So to find the domain, we take what's underneath the square root and set it greater than or equal to 0. But in this case, what we had was a polynomial inequality, not a linear inequality. So we had to make a sign graph. We set it equal to 0 and solved it to get our critical numbers. We plotted those 2 points on our number line to make our sign graph. We picked a test point and plugged it in and found out that at 0 it was positive. Cross a critical number, the sign changes. Cross a critical number, the sign changes. Or test a test point in each of your intervals, whichever you prefer. Once you've got your sign graph, then you can say, okay, I wanted to know where this was greater than or equal to 0. Those are the positive numbers, and so that's from negative 2 to positive 2. We're using brackets because we were equal to. If we had not had equal to right here, we would have been using parentheses, but because it was equal to, we used brackets. All right, so now we have the domain of f of x, and we have the domain of g of x, and we need to see where they intersect. Some of you can look at that and automatically know where they intersect, but if not, it might help to just kind of draw it out for yourself, okay? So I could go through and say, okay, if the first one exists from 0 to infinity, that's a bracket at 0 going off to infinity. The second one exists between negative 2 and 2. So that's a bracket at negative 2 and a bracket at negative 2 and the values in between it. So if I want to know where they intersect, where they overlap, where they both exist, that's only this piece right here between 0 and 2. So I could say, okay, their intersection is from 0 to 2. And it did include both of those values on both of those graphs, so I would include them with brackets in my answer. So we had from 0 to infinity, that was 0 to infinity. We had from negative 2 to 2, so that was negative 2 to 2. And so this was the only place where they both existed, where they both overlapped, was 0 to 2. So that will be the domain of my sum, my difference, and my product. I'll need to reevaluate my quotient because remember the denominator can't equal 0, and so I'll have an extra component to consider for the quotient. Okay, so when I look at my quotient, if my denominator cannot equal 0, we've already taken into account that this radical has to be greater than or equal to 0, and this radical has to be greater than or equal to 0. We've dealt with the radicals. The new thing that I have to deal with is that my denominator can't equal 0. So when I solved this up here, we said 4 minus x squared could be greater than or equal to 0. 4 minus x squared no longer can be equal to 0. That would give me 0 in the denominator, so I need to dump out that little piece from where I solved it previously. I need to take out the equal sign. It's the only change that I have to make. I can't equal 0 because that would give me 0 in the denominator. So if I take out the equal sign up here, what will that change about the answer that I got for my domain? If I take out my equal sign right here, what would that change about the answer that I got for my domain? Can't be equal to. How do we represent equal to? With brackets, right? So I have to take out the brackets. If I take out the brackets, what would I replace them with? Parentheses, exactly. So all I would have to do is change my brackets to parentheses. All right, so then let's think about the difference that that's going to make to the intersection of the two functions. The first one is still unchanged. It's still going from 0 to infinity. Nothing different about that at all. But instead of bracket negative 2, positive 2 bracket, we have parenthesis negative 2, positive 2 parenthesis. So I still have the same overlap right here between 0 and 2. 0 is included on both of those functions, so I can still have a bracket with it. But 2 is not included, so I need to change it to a parenthesis. So in the end result, it's just a tiny little change that instead of having a bracket with the 2, I have a parenthesis with the 2. That's the only change to the domain, but that's the reason behind it. That's why we have that one change. Okay. So again, like we said, adding, subtracting, multiplying, dividing, not so bad. Domain is where we really have to pay attention with these. Okay, so here is our homework for tonight on pages 116 to 117.